Hey everyone, welcome to our presentation on our root growth and rocky soil model. I'm Greta.
And I'm Hannah. So for our model, we wanted to talk about abiotic and biotic factors that affect root growth. So we asked the question, how do rock density and root branching affect root growth patterns? So to assess abiotic factors, we looked at the rock density. So we did a few different rock densities in our model. And then for root branching, we did different probabilities of the roots being able to branch out.
The way that we simulated root growth was we programmed a 40% chance that a root can grow down, a 25% chance that it can grow to the right or to the left, and a 10% chance that it can grow to both sides or bifurcate. And also roots can encounter rocks. Roots cannot go through rocks, and so if a root hits a rock directly, the root will stop growing. And we also used synchronous updates. In order to create the rock matrix, we based it on a percolation model. So we started with a matrix full of zeros and then changed those zeros to 2 or our new state of rock at different probabilities to create different densities of rock in the soil. And we also set the root to grow from the center of the top. So we can see here that with a rock density of p equals 0.1, none of our roots are getting very far. They encounter rock pretty quickly and stop growing. If we change our rock density to 0.05, we see a little bit more variability in what the roots look like. Sometimes they're still stopped by rocks pretty early on, but sometimes they make it further or even all the way down. If we change it again to 0.1, we see our roots making it all the way down to the bottom of our step size of 100 every time, as well as some difference in root density. We see some thicker roots, so more bifurcation.
So we also changed the bifurcation probability as another factor. So here we have a bifurcation probability of 0.3. And as you can see, the roots are making it all the way to the bottom of our cell, and they're also much thicker and more dense. And we can compare that to when we had a branching probability of 0.1, which is what we saw in our previous slides. And this kind of simulates a taproot system of a plant versus a fibrous root system. So it has implications for looking at different species and how they act in soils. And you can also note that for both of these cases, our rock density is 0.05, which we saw earlier. The root sometimes does not make it all the way down to the bottom of the cell at a rock density of 0.05, but it always consistently does at a branching probability of 0.3. And it's also much more dense, as you can see.
Our model definitely claims some assumptions like continuous root growth and a fixed growth rate. We know that in nature, this is not the case. Roots tend to grow differently during different seasons and encounter a myriad of other biotic and abiotic factors that change the way that they grow.
So for our future directions, we should challenge these assumptions and create a model or edit this model to incorporate different growth rates based on season or even species, and also have the roots be able to die on their own naturally rather than just when they encounter rocks. We could also incorporate other parameters that are outside of the scope of our model completely at the moment, such as is there a water table that the roots might encounter? What is the soil porosity even without rocks present? And then, what are the other disturbances like predators or temperature stressors that might affect the root growth all in all? And so our model has applications for understanding root growth in different environmental conditions, as well as for understanding root growth for different species, as we saw earlier with the species that have fibrous root systems versus a taproot system, and have that different rooting phenotype.
Thanks.
Thank you.